So we have a change compared to the original program. Yamina SIlva is replacing Antonio Parodi with actually different talk.
Good afternoon. I will present some preliminary results from the model we are running for the Central Andes of Peru, but actually it's not in very high resolution yet, but we are planning to run a high resolution model. First of all, I will speak a little about the major climate features of South America. We have in Southeast Pacific anticyclone that is, we have a cold current here and very huge upwelling. That's why it's a very cold water here. And we have the low level jet that comes from the east. It's very humid and very warm air from here. The precipitation over the Andes is related, of course, with this warm water from the Amazon, and it's cold air surface near the water surface, and the large-scale subsidence related to the anticyclone. And there's some episode for the dry episode. It's related with the anomalous westerly wind here. And that's why we have the climate in Peru. We have the Amazon, it's very huge precipitation until 7,000 millimeters per year. And the very dry coast, the coast of Peru, where the most of the people, the big cities are located in the coast, it's very dry, it's 5 millimeters per year precipitation. There's an medium precipitation over the Andes until 800 millimeters per year. There's our place to study, the Mantaro basin is located. It's the rainy season. Here it starts in September until April. The peak of the season, it's between January and March. Almost 50% of the precipitation comes in these months. Of course, over the Andes, because of the high altitude, the annual amplitude of temperature is also high. It's very cold in winter, and it's warm. It's more warmer during the summer. It's mostly related to the clouds and this time. The Mantaro basin is quite big for the Andes basin. Usually, the basins are very small. There. It's important because there is a hydropower energy comes from this basin. Also, there are important population there. Actually, there is a glacier here, but the main precipitation here is from the main water resource come from precipitation. In the valley, actually, it's small, but it's a great agricultural production here. Mostly of the agriculture in this area, it's directly depends from the precipitation. We run the WRF model for 2 domains now with 27 and 90 kilometers resolution. And there is a third domain with 3 kilometer resolution, but it runs only for some period. We ran only for 1 month to evaluate the amount of the biggest precipitation from 2000 until 2012. We use the initial and boundary condition, then set final analysis with 1 degree resolution. And for evaluating the precipitation, we use the tropical rainfall measurement mission from the satellite, the product 2A25, and also the station data in this 3 box. That's what we evaluated. Because we needed to have more resolution for the topography, we changed the default resolution from the model to the shutter radar topography mission, that's 90 meter resolution. And we use the land use actually from MODIS, but we are planning to change the land use also to more resolution. We ran the model with Thomson microphysics, Grell-Deviney cumulus, and unified NOAA land surface model for surface processes, and Yangtze University PBL. We used the TERREM satellite data for evaluate the precipitation, but actually it's not perfect data. I show here this is the topography. It's from the Andes until to the Amazon. This is the profile of topography here. And there is some stations. The bars are the station data, and the blue line is the TERREM precipitation. The TERREM tends to underestimate the precipitation over high latitude station. It's from this region from Peru. This is in the Bolivian altiplano. It's almost the same. This is for our region, for the Mantaro basin. We found this almost the same. This is the TERREM, the yellow line. The bars are the station data, and this is the WRF precipitation for this compared to this station. So one of the problems is that we have some data to evaluate the model. We have very few stations, especially difficult for the complex topography to have a good resolution that station data, has said Silvina in this morning. And we need actually to evaluate the satellite data also. This is the TERREM to evaluate the diurnal cycle. We use it also, the TERREM. It shows the early morning precipitation and the afternoon precipitation. It shows that most precipitation comes in the afternoon. It's quite well compared to the station precipitation. This is the bars, is the station precipitation. It comes in the afternoon between 16 and 19 at afternoon. And there is a second peak in the morning. Yes, this is just different kind of precipitation that we are evaluating. So this is the spatial distribution for every 3 hours. This is the TERREM. Here is our basin. There is no precipitation in the morning. It starts a little precipitation, and it's the maximum at 16 hours. It seems that it's quite well compared to the average precipitation that I said from a station. This is the WRF precipitation. The WRF is overestimated precipitation, or almost a factor by 4. It's because we need to use the same scale. We divided it by 4. The WRF precipitation also presents the maximum at this time at 16 hours, but it's shifted to the east of, compared to the trim precipitation. In this graph, the lines show the WRF precipitation divided by 2 compared to the station data. The maximum is 1 hour before compared to the station data. We analyze the fluxes. This is the vertically integrated moisture transport from the basin. This arrow shows the low level jet. It's quite well defined, the low level jet. It's no precipitation here. The shaded here is the convergence. It shows a huge convergence here in the 16 hours. It's related to the maximum precipitation. The convergence at 16 and 19, but it's not convergence in the other hours. It seems that the precipitation in this, the peak of the precipitation is related with the huge convergence. The flows come from the east, and from the west, and from the east. It's related to the circulation. We analyzed also the interannual variability for this period for 13 years that we ran the model in this box. There are not actually very well results because there is the dry years, only 2 or 3 years are well reproduced by the model. This it's some years later here for this year that was a wet year, and also a wet year here, but in the other years it's not what very well defined by the model. So what we have now, it's what we are planning to do is we have here in the laboratory that was implemented recently in the Andes. We have different instruments to measure these atmospheric parameters, not only the conventional temperature and precipitation. Also, we have here the fluxus tower to calculate the fluxes, the sensitivity for the latent fluxes. Also, we have a densitometer to calculate the distribution of the precipitation, or the solid precipitation, or wet precipitation, or water precipitation, and 2 radar. It's the cloud precipitation radar and the boundary layer tropospheric radar, or wind profiler. And we will use this instrument just to understand all the processes that related to precipitation and the energy balance and the water balance in this region, in this observatory, and then understand better the model. So this is an example for these 2 hours. This is the radar data, this is the reflectivity. We have some precipitation here, and here also some convective precipitation, and we have compared it with the densitometer. We are comparing different data for precipitation, as the conventional data with the densitometer and the radar data, and also we are using the GPM satellite to evaluate the precipitation. Yes. So what we need now is to calibrate the precipitation that is produced by the satellite from the GPM using the Marshall-Palmer equation that's needed. We have the relation between the rain rate and the reflectivity, and we have this data from this is the reflectivity from the densitometer and from the radar, and that's why we use from different precipitation, the convective precipitation and the stratiform precipitation. This is an example. We have one day what is the wind profiler data. It's the vertical velocity, and we can see here, and then it's the up and down air here, and we could see in the radar data there's a convection here, there's a precipitation here, and it's we can see the clouds, and we can see the precipitation in this data. So we are now interested in the microphysics of the clouds and the precipitation using this data. So in summary, we can have the world. It's very nice to have a model that we can run for this area, but now it tends to overestimate the precipitation by factor 4 respect to the terrain, and by 2 respect to the ground precipitation. The diurnal cycle is quite well simulated by the model. The model reveals poor skill in reproducing the interannual variability of precipitation across the basin. And also the satellites tend to underestimate the precipitation over the Andes, in comparison to the observational data. What we need now is really high resolution models, almost 300 meters to the valley, to study the physics of storm and cloud and precipitation over the Andes. Thank you.
Maybe time for one question, if there is any. So I have a question. So did I see correctly that actually this convection scheme was able to catch the diurnal cycle? This GREL...
the GREL scheme.
scheme.
Yes, it's 9 kilometers, it's a convection parameterization.
Oh, okay. So I guess in some ways it depends where you're running these convection schemes, whether you catch the diurnal cycle or not. Okay, thanks very much, Yamina.